So this is Mark, and in response to Black Pen, Red Pen, and his awesome lazy AC method for factoring quadratics or factoring trinomials, I wanted to give this proof. There was some interest in why does this sort of crazy method with several what I call questionable steps actually work. So I've heard this also called the T method on another factoring trinomials video on YouTube. So in this video, I'm just going to give a quick example of how to do the lazy AC method. I'm going to try to keep this quick, but just in case any of you didn't see the original video, you can sort of see how this works. Then I'm going to provide the proof. That's the main event. And then I'm going to also give a caveat, like a little warning about when or how not to use this system, because it will give you a wrong answer if you're not a little careful. But it's no reason not to use this awesome, I think the best method for factoring trinomials that I've ever seen. So first, quick example. We're going to take 5x squared plus 18x minus 8. You may recognize this as the trinomial that Black Pen, Red Pen left us with at the end of his video. Very factorable according to this method. You can do it by another method, but there's a little bit of trial and error. And as usual, what we're going to do is we're going to make an x, and then we're going to take AC and b, and we're going to place those numbers in the top and bottom parts of the x. So in this case, AC equals 5 times negative 8, which equals negative 40. B equals 18. And now what we're going to do is try to find all the factors of negative 40, and I'm going to list them here. And this is the normal method of factoring a trinomial, so you may be used to this idea already. And if you are used to this idea, it may jump out at you fairly quickly that if we try to find the factor pair that adds up to 18, that factor pair is 20 and negative 2. And so from factoring basic trinomials with 1 as a, we know that we're just going to put those two numbers down inside the parentheses, and we would be almost done if it weren't for that 5 coefficient, and that's kind of making our lives difficult. So at the risk of totally messing up what we're doing, we're going to take 5x inside both of those parentheses. This is what I call the first questionable step, because if you step back, you can already see we've got the wrong answer. What we have now can't possibly FOIL out to the trinomial we're starting with. But according to the method, what we're going to do next is inside of each pair of parentheses, factor out the greatest common divisor. Second pair of parentheses we don't really have to do anything with, but the first pair, we notice that we have coefficients of 5 and 20, so we divide both of these terms by 5, which is the second questionable step. And somehow all of this questionable math seems to work out, because look what happens. When the smoke clears, the answer we get is x plus 4 times 5x minus 2, which actually is the correctly factored form of this trinomial, which I think deserves an exclamation point right there over that equal sign. How do we get there? And this method always seems to work. So there was a call out there for, like, what's the proof? Does this really always work? If it always works, it should be provable, right? So what follows is I'm not doing a very formal proof, but I want to think of it as more of an explanation. And I will leave the very formal proofs to the real mathematicians out there rather than just the explaining folks like myself. So here goes. We're going to start with a trinomial ax squared plus bx plus c, which is about as generic for a trinomial as I think we want to get. Couple of things about this trinomial we're working with. The whole point of this method is to start with a trinomial that is factorable into integer coefficients. So the assumptions we're going to make here, I think this is pretty fair. We're going to say that a, b, and c are all integers, and that this trinomial in fact can be factored into integer binomials. And if that's true, then there better be a final answer that looks something like px plus q times rx plus s, with p, q, r, and s all integer values. Assuming that's the case, this method should work. But that actually gives us a little bit to work with, doesn't it? Because if this is going to be the end value, the value that we're supposed to get at the end of this proof, what this means is that we can look behind the curtain just a little bit and FOIL out this result to take a look at its component parts. So it makes it look more complicated at first. We have prx squared plus psx plus qrx plus qs. And now we can combine the middle two terms to make it look even a little more complicated. Prx squared plus the quantity ps plus qrx plus qs. This may look less attractive, but it actually is going to help us. Because remember that our original assumption is that we started with a polynomial in the form ax squared plus bx plus c, and now we've really got another version of that, don't we? And so what we know is that a equals pr, b equals ps plus qr, and c equals qs. Okay, well, how does that help us? So given all that information, now we're going to start officially the lazy AC method and see where it takes us. We're going to make our x, we're going to fill in AC and B values. And what are those AC and B values? Well, AC is PQRS. We multiplied A times C, and I just put things in alphabetical order. We don't really have to do that, but that's just how I roll. B value, PS plus QR. Okay. So now according to the method, what we're looking for is two values that multiply to PQRS and add up to PS plus QR. And that really doesn't take much work at all, because if you step back and look at this, the only possible answer is PS and QR. Obviously PS and QR multiply out to PQRS and add up to PS plus QR. So according to the method, we're going to put those values right into the parentheses. And then, remembering our first questionable step, we're going to take the a value and attach it to x and place it into both sets of parentheses. And in this case, that a value is PR. Okay, so moving on, now according to the lazy AC method, within each set of parentheses, we're supposed to divide out the common factor. In the first set of parentheses, common factor is r. In the second set of parentheses, the common factor is p, which again I call a questionable step, but surprise, surprise, when we do this, what do we get? We get px plus q times rx plus s, which is exactly what we wanted to get. So it seems that this works for all values a, b, and c, provided first, which I said up front, that this trinomial is indeed factorable down to integers, because this whole proof is premised on we're dividing out integers, right? Greatest common divisors. But there's a second unstated premise, and that is that the three integer coefficients a, b, and c were not mutually divisible by some integer other than 1. So why does this matter? If we're going to be dividing things out on the pretty much last step, we want to be careful about this, and this brings me to the caveat. So this time for my example, I'm going to use 10x squared plus 36x minus 16. And this should look a little familiar because it's simply the original trinomial that we used in the first part of this video, but multiplied by 2. So we know how this story ends. It should end up factoring as 2 times x plus 4 times 5x minus 2. So keeping that in mind, let's just run our method. In this case, AC equals 10 times negative 16, which equals negative 160. B equals 36. I won't belabor this step, but the two numbers that multiply to negative 160 and add up to 36 are 40 and negative 4. So those are the two values we place inside the parentheses. And as usual, we use our AX value, in this case 10x. So now, according to the method, we divide a common factor of 10 from the first set of parentheses, a common factor of 2 from the second set of parentheses. And what do we get? We get x plus 4 times 5x minus 2. And step back for a second and notice that that is the wrong answer. That is not the properly factored form of this trinomial. So what happened? Well, what happened was we threw out the baby with the bathwater and factored out a factor of 2 that we shouldn't have. And why did that happen? That's because we started with a trinomial that had a factor of 2 that could have been factored out from the beginning. So the moral of the story here is factor out the GCD of the coefficients, if one can be factored, before applying the lazy AC method. And feel free to use this method for all your factoring needs in the future. I think it's the best method out there. And hopefully this video was helpful and made some sense of this seemingly crazy method and helps you sleep a little easier at night recommending this to your students. Yep, it really does work, as long as you do the factoring of the integers first.